So this is a preliminary to the problem that we want to solve today. Previously, back in Chapter 2, we looked at limits. We defined the limit as x approaches a of f of x. The idea behind that, the intuitive definition is, when x is close to a, f of x is close to some number L, if that limit exists. We're computing a different kind of limit today. It's a limit as n approaches infinity, or we could be using x here instead of n. We're not asking what's happening to our function when x is close to a number. We're asking what's happening to our function when x is increasing without bound, getting bigger and bigger and bigger. This is in section 2.6 in your book, and we did not talk about it at that time. I like to talk about it when we really need it, and that's right now. Okay? Let's use our common sense. When n gets bigger and bigger and bigger, what's happening to 1 over n? Let's make a table of n and 1 over n. 10, 100, 1,000. 1 over n is 1/10, 100th, 1,000th. In other words, 0.1, 0.01, 0.001. So what do you think the limit as n approaches infinity of 1 over n is? When n approaches infinity, when n gets larger and larger and larger, increases without bound, what's 1 over n doing? It's approaching 0, isn't it? You can make the quantity 1 over n as close to 0 as you please just by making n sufficiently large. If you look at a graph of f of n and 1 over n, I'm going to make the graph continuous. It looks something like this. There's a horizontal asymptote at the horizontal axis. The bigger n is, the closer 1 over n is to 0. Often in this discussion of computing limits as x approaches infinity or n approaches infinity, you talk about horizontal asymptotes. If you're interested in that, you can go back and read details in section 2.6. Okay? This is a common building block that you need to understand. Limit as n approaches infinity of 1 over n is 0. That should make sense to you. It's something you'll use again and again. So make sure you understand that, but remember that. Okay. Limit as n approaches infinity of n. When n gets bigger and bigger and bigger, what's happening to n? We say that limit is infinity. The limit doesn't exist. In other words, a limit existing means that the limit has a finite numerical specific value. But we're more descriptive by saying the limit's infinity. In other words, the bigger this n is, the bigger this n is. In other words, if you look at a graph of f of n equal n, it's just the graph of f of x equal x, isn't it? The bigger x is, the bigger the y-coordinate is. Now, limit as n approaches infinity of 1 over n squared plus n. What do you think that is? What's your intuition? Write something down. What do you think? Is it 0? It is 0. As n approaches infinity, n squared plus n is going to approach infinity. And so, in fact, the bottom is getting bigger a whole lot faster than the bottom is getting bigger here. So this limit, this quantity, 1 over n squared plus n, is going to go to 0 faster than the quantity 1 over n did. Okay? Now, you can do this problem like this. You can write that as limit n approaches infinity. You can divide top and bottom by n squared. You can divide top and bottom by n squared. In other words, by the highest, I divided top and bottom of this by the highest power of n. Okay, and now this is just limit as n approaches infinity 1 over n squared over 1 plus the limit as n approaches infinity of 1 over n. Now, when n gets bigger and bigger and bigger, 1 over n squared is going to 0, right? Go back up to the top. Go back up here. When n gets bigger and bigger and bigger, 1 over n goes to 0. So 1 over n squared would certainly go to 0 even faster. Right? Here's n, and here's 1 over n squared. 10, I get 1 over 100 equal 0.01. 100, I get 1 over 10,000, 0.00001. As n is approaching infinity, 1 over n squared is approaching 0. Okay? And earlier we said the limit as n approaches infinity of 1 over n was 0. So this is just 0 over 1, which is 0. Notice we get the same result as we originally wrote. And you really don't have to do this work that I've just done. Just think about it. When n gets big, n squared plus n is going to get big. It's going to go to infinity. The reciprocal is going to go to 0. Okay. How about this one? Limit as n approaches infinity, n over n squared plus n. Now this one might require a little bit of work like we did at the bottom. This one might actually require a little bit of work. Let's divide top and bottom by the highest power in the expression, and that's n squared. Okay, now let's take the limit as n approaches infinity of 1 over n here in the top. Let's go back up here. Limit as n approaches infinity of 1 over n is what? 0. And I have limit in the bottom as n approaches infinity of 1 over n. That's 0. So I get 0 over 1, which is 0. So this second limit here, this one, I don't know why I called it the second limit, it's the fourth one I'm doing, is 0 also. How about the limit as n approaches infinity? And by the way, I could confirm this, that the limit as n approaches infinity of n over n squared plus n is 0 by making a table of values. The bigger n gets, this expression would get closer and closer to 0. Okay. Limit as n approaches infinity of 2n plus 1 over n minus 3. Highest power of n is n to the first. I'm going to divide top and bottom by n. I divided top and bottom by n. 2n over n is 2. 1 over n is 1 over n. N over n is 1. 3 over n is 3 over n. As n approaches infinity, 2 stays 2. But 1 over n is going to 0. Remember, much of this comes back to this first limit up here at the top, that building block I said you needed to remember. As n approaches infinity, 1 is staying 1, but 3 over n is going to 0. So I get 2. And if I made a table of values of n and 2n plus 1 over n minus 3 and let n go to infinity, so let n get bigger and bigger and bigger, you could compute these values and you would see that they're approaching 2. And finally, the limit as n approaches infinity of 5n squared over n plus 1. Highest power of n here is n squared. I'll divide top and bottom by n squared. Now notice limit as n approaches infinity of 1 over n is 0. Limit as n approaches infinity of 1 over n squared is 0. Oops, I can't divide by 0. This limit does not exist. And if you go back to the original problem, look at 5n squared over n plus 1. The top's going off to infinity, the bottom's going off to infinity, but the top is doing that faster than the bottom because n is squared. So some people say this limit is infinity because if I make a table of values, what's happening to this would be that it is increasing without bound. The limit doesn't exist, but the way it doesn't exist is that these numbers are getting bigger and bigger and bigger. So we describe that by saying the limit's infinity, even though the limit doesn't exist. Okay, do you notice any patterns? Look back through these problems and see if you notice any patterns. How about if the highest exponent in the numerator, the degree of the numerator, is greater than the degree of the denominator? That happened where? Here, the highest power in the top is greater than that of the bottom. That also happened here in the second one, because n is n over 1. What were our results? We got infinity, didn't we? But how about if the degree of the top, the numerator, is less than the degree of the denominator? Where did that happen? That happened here, here. Degree of numerators less than the degree of denominator. What was our answer for our limit as n approached infinity? It was 0 each time, wasn't it? 0, 0. That's always going to be true. If you're taking the limit as n approaches infinity of a rational expression, the degree of the top's less than the degree of the bottom, the quotient is going to go to 0. Because the top, that's good enough. And how about in our remaining cases? How about another case of that was also this one at the top also. All right, how about our remaining cases? These, this example limit as n approaches infinity of 2n plus 1 over n minus 3. Look at the leading coefficients. The coefficients of the highest power in top and bottom, 2 and 1. And what was our limit? 2. That will always happen also. For example, the limit is n approaches infinity of 8n to the 7th plus n squared plus 3 over 15n to the 7th minus 1. The degree of the numerator is 7. The degree of the denominator is 7. This limit is going to be 8 over 15. You could confirm this by dividing top and bottom by n to the 7th. Taking the limit of each term, you'll end up with 8 plus a bunch of zeros over 15 plus a bunch of zeros.